Okay, we left off talking about binary search. And so let's review. Linear search, I start at the beginning of some collection and I say, is this the thing I'm looking for? Yes or no? No? All right. Is the next thing the thing I'm looking for? Yes or no? Et cetera, et cetera, et cetera. And if I had a list of n things, worst case scenario, how many things do I have to look at? All of them, all n of them, exactly. And if I double the input size, how much more work do I have to do? N more, so 2n work in total, yeah. Right, so the point of this was, with a linear search, the algorithm does a linear amount of work, but also the amount of work that the algorithm has to do as a function of the input size n is linear. Like the amount, if I double the input size, I double the amount of work. If I quadruple the input size, I quadruple the amount of work. That's it. With binary search, we saw something a little different. We played that game where I said pick a number between 0 and 1023, and I told you I could get the number in 10 guesses. If I was doing a linear search, how many things would I have to guess to guarantee I find the number? Between 0 and 1023. With a linear search. 1000, all of them, yeah, all 1024. We include 0. But with a binary search, I was able to do it in 10 guesses, right? Actually, I did it in less, but I'm guaranteed to get it in 10. But the trick was, it required that the data that I had, it required that I was able to say higher or lower, right? I started by guessing 512. And then if I was wrong, I said higher or lower. Which means that the data had to be sorted. I had to be able to know which way the thing I was looking for, which way it was. Was it guaranteed to be in the left, the less than pile of 512, or is it guaranteed to be in the greater than pile of 512? The data was sorted. It had a sorted order. Think of pages on a book. Those pages are sorted in numerical order. So if I turn to page 512 of a 1024 page book, I turn to page 512, okay? All the page numbers that are less than 512, I'm a mirror right now, are over here. And all the pages that are greater than 512 are over here. And if I told you to turn to page 700, which side do you look at? Do you look at the side with the numbers less than 512? No, that's stupid, because the number 700 is not less than 512. The page you're looking for must be on this side. And when I make that decision, pay attention to this. When I make that decision, I'm looking at page 512, and I'm looking for page 700. I know it must be over here. There's roughly 512 pages over here and 512 pages over here. And I'm making a decision to continue my search here. How many pages did I eliminate from my search now? Half of them. I eliminated 512. I didn't need to look through this 512 anymore. I only need to look at this 512. So I can eliminate half of them. So now I have the pages. Let's say I was looking for the page just to make my life a little easier, let's say I'm not looking for page 700 anymore, I'm looking for page 300. So I'm looking at page 512. I know 300 is less than. So I eliminate all the pages 512 and up. That's half of all the pages that were there. I made I looked at the data once, and I was able, I queried the data once, and I was able to eliminate half of the data. With a linear search, when I start at the beginning and I say, are you what I'm looking for? And if you say no, how much data did I eliminate from my search? Just one. Not just one. It's a linear search. I look at the first thing. Is it what I'm looking for? No. Well, that must not be it. With the binary search, I confirm the thing I'm looking at is not it, and then I know which side to carry on looking. So I'm looking for page 300. I'm looking at page 512. I know 300 is over here, so I eliminate this 512. What should my next guess be? 256. So I turn to page 256. I just happen to turn to page 256. And I go, okay, great. I'm looking at page 256. I have page numbers 0 through 256 over here, and 256 to 512 over here. And I'm looking for page 300. Which side do I look at? The bigger side, because 300 is bigger than 256. So I carry on. And then I would, at that stage, how many pages did I eliminate from my search? I've got 256 here and 256 over here. How many did I eliminate? 256. Half of the remaining data. Then I would do it again. And I would make a decision. It is either on this half or this half. And every single decision I make, I eliminate half of the amount of work. A linear search, I eliminate one unit of work. I investigate one thing every time I look at something. With a binary search, I'm able to eliminate half of the data at a time. Now, realistically, if you're doing this with a book, you're looking for page 300, you're not going to be like, well, I'm going to start by looking at page 512. No, obviously you're going to try to eyeball it. You open it, and if you look at page 3 and you turn to page 350, okay, you don't go halfway between. You kind of eyeball. You're like, that's probably about 50 pages. You check. Maybe you got to turn a few more pages, and you're good to go. But this binary search is a far more generalized version of what you already do. So whether you like it or not, you're already familiar with this algorithm. You just probably never really thought about it explicitly like this. With the linear search, I'm going to sound like a broken record, but let's reestablish some things here. Input size n, with the linear search, how many things do I have to look at? N. If I double the input size, how much more work is there? Double more work, yes. Perfect. With a binary search, input size n, how much work do I have? Yeah. Who here just heard the word log and was like, oh, screw it, I'm done. Yeah. Here's the good news. Computer scientists, we only like log base 2. And log base 2 is easy. So just to refresh everybody, let's take a step back. If I told you to add 1 to a number 5 times, right? What did I effectively do? If I said add 1 to a number 5 times, you just added 5, right? So let's take a step back and think of the simplest the simplest numerical operation we can do. It's count. Okay? Just add 1, increment. That's the simplest thing we can do. And if I say increment 5 times, you go, well, that's just plus 5. And you're right. We came up with this addition operator, which generalizes this like add 1 some number of times, right? But what happens then if I say, okay, add 5 times? Right? So you say 5 plus 5 plus 5 plus 5 plus 5. But then what do you say to me? You're like, well, that's just multiplication, right? So addition is like this generalization of a counting thing. And then multiplication is this like, not generalization, but this like step. Multiplication is a step of doing multiple additions at a time, right? Please tell me you know this. But of course, what happens if I say do multiplication some number of times? What operator do we use in place of that? Exponent, right? So if I say count, like increment something 5 times, well, that's really just like plus 5, right? And if I say add 5 times, you're like, well, really that's just multiplication, right? And if I say do 5 times, like do 5 times 5, we're now looking at exponent, right? This isn't shocking, right? It's just repeating these operators. We come up with a new symbol to mean that. And of course we know subtraction is like the opposite of addition, right? And we know that division is like the opposite of multiplication, right? We agree? Well, log is just the opposite of like the exponent, right? It's the opposite of that. So don't let log spook you. Just make sure you know what it means. And the good news is, yeah, we only care about log base 2 in computer science, almost always, only ever care about log base 2. So when I say log base 2 of 10, what does that mean? Right? So what is let's 1024 for simplicity. Log base 2, so 2 to the power of 10 is what? 1024. So log base 2 of 1024 is 10. Log is like doing the undo. Log is like the undo of like the power of. How many times do I divide this by 2, right? 1024 divided by 2 is 256 divided by 2. So 1024 divided by 2, 256, no, 512 divided by 2 is 256, divided by 2 is 128, divided by 2 is 64, divided by 2 is 32, 16, 8, 4, 2. It gets us down to like 1. Right? And how many steps was there? It's like the opposite of doing, okay, 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is, I'm just doing it the other way. Okay, that's all it is. And if you're still spooked by it, you are not overcoming your terrifying math classes where log scared you. It's really not that bad, trust me. So it's basically the division of. And you might say like, oh, okay, so it's like dividing by 2 over and over and over again until you get down to like one thing. But that's like what binary search was doing, right? We're like dividing by 2 the amount of information we had to look at every time. So if I had n things to look at and I did a binary search, not n things to look at, but if I had a collection of n things and I could do a binary search on it, the total amount of work I would have to do is log base 2 of n. Now let me ask you a question. What is, if I said I've got two algorithms that you can follow, and I've got a pile of 1028 things here that are sorted, and a pile of 1024 things, pardon me, are sorted. And I said you can do one of two algorithms. If you follow a linear search, you're going to have to look at all 1,024 of them to guarantee if you find what you're looking for or not. Or if you follow the binary search, you need to only look at 10. Which one are you going to want to do? The one that requires way less work. Way less work. It's not like, oh yeah, I guess it's better. It is hilariously better. A binary search is so much more like efficient of a search than a linear search. But there is the catch. The data has to be sorted. I have to be able to say, well, which side of my collection should I continue looking through? If it's not sorted, I can't do a binary search. If it is sorted, I can do a binary search. So if our data is sorted, we can search through it way faster than we could if it wasn't sorted. So let me ask you this. I'm going to go back to concrete examples. And again, I sound like a broken record, but these are good concrete examples. If I gave you a list of 1,024 numbers and told you to do a linear search, how many things do you have to look at? Say it out loud. 1,024. So if I doubled it to make it 2,048, how many things do you have to look at? 2,048. Great. Now, if I told you to do a binary search on sorted data of 1,024 things, how many things do you have to look at? 10. If I doubled it to 2,048, how many things do you have to look at? 11. When I doubled the input for the linear algorithm, I doubled the amount of work. When I doubled the input for the logarithmic algorithm, I only had to do one more unit of work. Way better. So if you're in a position, like if I gave you sorted data, and I said, okay, write code to search through this data, and you come with a linear algorithm, you've got a terrible algorithm. When an alternative is binary search, and the reason it's terrible relative to binary search is the runtimes, the computational complexity. A linear time algorithm, don't get me wrong, if you have an algorithm for some general problem and it's a linear time algorithm, that's pretty good. But if there is an option to make it, someone found the wrong class, it looks like. If you have an option for an algorithm to be logarithmic time, it's going to be like that's what you want. And doing a linear algorithm is a dumb idea if there is a logarithmic one that'll do the same thing. But there's always a give and take. A linear search is always going to work, whether your data is sorted or not. A binary search will only work if the data is sorted. But if it is sorted, you want to use it. Any questions about any of that? I'm going to say it again. You all know a binary search. You've all done this before. Every time someone's ever told you to turn to a page in a book, you've done this idea. Where you eliminate chunks of data at a time instead of one thing at a time. And that's the trick. That's why it's so much better. Is every time I query my data, I'm able to eliminate half of the things. When you're just willy-nilly turning to a page, it's not going to be like half or half or half, right? But you're going to eliminate chunks of things at a time, and that's what makes it faster. Almost always in computer science, just going forward, if I say log, I almost always mean log base 2. Okay? When I say exponential, I almost always mean 2 to the power of something. So, and often too, if you see like log written in any like computer science textbook or anything, it's going to be log base 2. Like they won't put in the 2 a lot of the time just because it's a given that, okay, it's log base 2. There are exceptions, but it's almost always log base 2. Okay. Any questions at all about that? All right, blah, 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 complexity analysis. Yeah, we just did all that. Originally linear haystack, yeah, okay. Yeah, this is just explaining everything. Okay, so raise your hand if you're planning on taking 162. Cool. A lot of people at this stage, you know, you're excited for 162, and you should be. 162, in my opinion, is a much better course than this one. It's a lot more fun. You learn a lot more interesting things, so you should be excited. But a lot of people get spooked when they're like, well, we're changing programming languages. I learned Java, or I learned Python. Now I need to learn Java. I don't want to learn a new language. That's going to be scary. And I will say, for the most part, most students at the start of the semester, they admit that what they're struggling with is Java. But after a week or so goes by, they will all admit that, no, it really wasn't. I thought that's what I was struggling. It was nothing. So I'll warn you, you're probably going to feel like it's annoying at first, and yeah, there is a bit of a learning curve that you kind of got to get figured out. But it all comes down to just some little differences in syntax. The algorithms are the same. The syntax will be a little different. And that's it. So when people are talking about like different programming languages, a lot of the time, like experienced programmers know that, oh, different programming languages really aren't very different at all. There are programming languages that are very different, but for the most part, of all the popular languages, they're all very, 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 very similar. Hilariously similar, actually. Python's actually probably the most different from the others than the others are from each other, but you'll see. There is some syntax stuff, fine. And just for a heads up, the first like week or so of 162 is, here's everything you learned in Python, but in Java. And assignment 1 in 162 is the like basically identical assignment as it is in the last one in 161, but in Java. So you get some time to work out those kinks there. But let's take a moment and look at some code. Here is a linear search in Python. All right, I know we've talked about this a lot already in this topic even. But haystack needle for I in range of the length of the haystack, fine. We're going to loop over each index for that list. If haystack at index I is the thing I'm looking for, return true. If I ever get to the end of the for loop and I never found it, meaning I never returned true, return false, because it must not be there. Any questions about this? So let's break down this algorithm. First of all, actually, let's go a little bit further and break down this Python code. We start with the function definition. The first line there is just the name of the function and the parameters, right? And then inside of it, we've got a loop, a for loop, that's going to go from 0 to the length of the list minus 1, right? And then we have an if statement that just checks if the thing at index I is what I'm looking for. It's just an if statement. If the thing at index I, if haystack at index I is equal to needle, we return true. And if we ever finish that loop and we never get to the end, and we never return true, we get to the end, never return true, return false. That's the algorithm. No, that's the Python code. Really, the algorithm is look at each thing in the list and compare it and check if it's the thing you're looking for. That really is the algorithm. That's the idea. But when you look at the code, I was a little bit more explicit in what the code was saying. Start with the function definition. This code doesn't even need to be in a function, but I put it in a function. For loop to iterate over the contents of the list. Check if each thing in the list is equal to what I'm looking for. Return true, otherwise return false if we get to the end without returning true. So far, so good? So let's take a moment and look at The exact same algorithm, but this is Java. And you look at this, and your knee-jerk reaction is like, wow, yeah, that's very different. But let's take a moment and realize that it isn't. That first line there, that's the function definition line. Sure, it says public static Boolean, right? Public, we don't need to worry about right now. Static, we're not going to worry about right now. Boolean, linear search. What do you think the Boolean means? It's the return type. In fact, I should probably add the type hints to this here, because there'd be a little arrow bool, right? So this is a function that's going to return a Boolean. Its name is linear search. In Java, we use camel case, not snake case. So that's why it's written a little differently. And then we have haystack and needle. But with Java and a lot of other languages, they're a little bit more, you have to be a little bit more explicit with your types. So I'm going to have, for our purposes, you could think of this as an integer list, a list of integers. All right? A list of integers called haystack and an individual integer, needle. Right? If we go and look at the Python code, there's syntax differences, but in terms of what it means, in terms of its semantic meaning, it's just the definition line of the function. Name of the function, parameters. Name of the function, parameters, but we need the types in Java. What's the next line? Well, that looks different. But let's take a moment and let me explain what it means, and then you'll realize it's not different, it's just syntax. It's not semantics, it's syntax. This is a for loop written in Java where you're using an integer I, and all this means is I starts at 0, and while I is less than the length of the haystack, I can ask that. So in Java, that's really not a list, it's an array. We'll learn all about arrays in a month or so. But I can ask the length of it, just like, so in Python, if I want the length of my list, I say len, the list. In Java, I just say the list.len, okay? Or length. And then every time the loop executes, I increment I by 1. Just the for loop. Start at 0, go to n, counting by ones. That's it. If haystack at index I is equal to needle, this is even more obviously the similar line. Line 3 in both, the biggest difference is the parentheses and the brace, the squiggle bracket. You don't need the squiggle brackets in Python. And if you're looking at this and you're like, oh, I need to worry about these braces in Java, trust me, you're going to love it. Usually, like one of the number one things people will complain about, experienced programmers will complain about Python, is the lack of braces. Programmers like our squiggles. So don't worry, that shouldn't spook you. And if that statement's true, we return true. Look at the difference in the return line. What's the difference there? Capital T. Oh, and in Java, we must end our statements in semicolons. So, okay, return true, semicolon, whatever. End the if, end the loop, line 7, return false. Yeah?
We don't capitalize true and false?
Not in Java. Why? Because. I don't know why. In fact, I'm pretty sure Python's the weird one. I'm pretty sure like in all the other languages, they're all lowercase. All of the other similar languages are all going to be lowercase. Python's the weird one that decided to capitalize them all. Don't ask me why. Someone somewhere said, I like capitals, and that's what we do from now on. There is obviously syntactic differences here, but in terms of what it means, definition of the function, loop over the contents of the array, check if each thing in the array is the thing I'm looking for. If it is, return true. Otherwise, keep going. If I ever get to the end, return false. The algorithm is exactly the same. The algorithm is identical. The syntax is what's different. Any other questions about this? If you end this course and I say, explain to me a linear search, and you can do it in Python syntax, you don't know a linear search in Python. You know what a linear search is. And then if you need to implement a linear search in another language, it's just an exercise of figuring out the syntax of that other language. If you're ever in 162 and you're like, I can't remember how to do a loop in Java, I'm screwed, I guess I must give up. No, you're a terrible programmer, not because you didn't know how to do a for loop in Java, but because you didn't think to go to Google and say, for loop Java? And find literally billions of examples of for loops in Java. That's why you would be a bad programmer, because you didn't think to do that. Here's C#'s linear search. I'm going to zoom out. No. Here's a linear search in C#. C# is another programming language. Here's the funny thing about this one and the one in Java. They're identical. The syntax is actually the same. Entirely different programming language. The algorithms are the same. But in this particular example, the syntax is literally identical. Public static Boolean, linear search, int array, haystack, int needle, squiggle. The for is the same. If is the same. Even the t is lowercase and true. We end with semicolons. They're different programming languages, but they're really not different. Here it is in C++. Now, the biggest difference here, there's syntax differences. Here, we didn't say Boolean, we said bool. Okay. We didn't need public static in front or anything. Fine. And I guess in C++, we'd use a vector. We'd call them vectors instead of like lists. But a vector called haystack and a needle. And then there's the for loop. Oh, I guess instead of haystack.length, it was haystack.size. And it's not an attribute, it's a method, because I could tell because it's got parentheses next to size. But basically, ask the collection, what's your length, what's your size, and loop from 0 to size, counting by 1. If that statement's true, return true. If I ever finish the loop, return false. Syntax is a little different than Java and C#, but it really isn't. And here it is in C. The funny thing about C, at least doing this in like pure C, so C, by the way, is an old programming language, very old. But it's a pretty big deal one. It's important. In fact, C basically, all of these languages that I'm showing you so far, people would call them C-like. Basically, the syntax of how C did it is set like the standard. So they're all trying to be like C. But here's C. And the biggest difference here is the arrays in C don't know how big they are. You can't ask an array, hey, how big are you? You kind of can, but we're not going to do that right now. So instead of asking the array how big it is, we just have to know how big it is. And that's what that third variable is there, n. It's just going to be the length of that array. So for I to 0 to n. So instead, here we explicitly say n instead of asking the collection how long it is. But other than that, function definition, for loop from 0 to n, counting by ones, the if statement to check if the current thing is the thing I'm looking for, return true, return false. It's the same. Obviously, Java, C#, C++, and C, I would say are more similar to each other than Python, but having looked at those things, they're really not different at all. They're not. And if you're not agreeing with me, this is what a programmer would say is a different programming language. This is a programming language that is different. This is Haskell. It does a linear search. If I told you in 162 we're using Haskell, yeah, be freaked out. Because it's different, and it is different. But the difference, like this is what a programmer would say, is like, yeah, there's a difference in the languages. To be clear, and I'm not, let me give me a moment, I'll come back to what I was about to say. That a programmer would be like, yeah, okay, these languages are different. And if you say like, how different is C and Python? They'd be like, they're not. Yeah, there's differences, but they're not. This is different. So if you're worried about changing languages and you thought we were going to make a leap from something like Python to Haskell, no, we're going from Python to Java, which maybe it'll take you a week to get used to the differences, if that. No, this is Haskell. And actually, what time we got? This right here, I would say a lot of programmers would say, and this is a weird concept to explain, but there would be a lot of programmers, computer scientists that would look at that code and be like that is like aesthetically beautiful, that algorithm right there. It really is. I'm not trying to be silly. Like, I look at that and be like, oh yeah, that's nice. That's beautiful. At the end of the day, the algorithm is basically the same as the other algorithms. There is a bit of a nuance difference, fine. But yeah, the syntax is very different. The underlying algorithm is basically the same. Syntax is clearly wildly different. But that right there is gorgeous. Who wants to know what it means? Put up your hand. Of course you want to know what it means. Let's explain what it means. The first line is just like the definition line of the function. All right? This is saying I've got a function called linear search. All right? And it's an equation of something of type A. Now, this is a strongly typed language, but what this means is it's some type A. I don't care what the type is, but there is a type A. And this is a function that takes a list of things of type A and a single thing of type A. If A wasn't, think of A as a variable for a type. You could have a list of integers and an integer. You could have a list of strings and a string. You could have a list of booleans and a boolean. It doesn't really matter. But this is a function on type A that takes a list of type A and a single thing of type A, and it gives you back a boolean. All right? That's what that first line means. That second line means, okay, let's establish something that should be true. I need a volunteer. Who's brave? You better be really brave. You're going to be very brave, okay? Okay, I'm going to give you a list. And I'm going to ask you to tell me if the list contains my favorite number. And I'm not even going to tell you what my favorite number is. Okay? But you better be able to tell me if it's in this list or not. Who here thinks if he can? I told him, and I guarantee you he can. But you might not believe me. Let me be clear what I'm asking him. I'm telling him I'm going to give him a list. And I need him to tell me if that list contains something that I'm not telling him. You better tell me if my favorite number is in here. Do you know what my favorite number is? But I'm going to guarantee that you can tell me if it is or is not in the list I'm about to give you, okay? Who here believes me? You believe me because you trust me, right? But you should be skeptical. So here it is. Here's a list. It's empty. Is my favorite number in that list? How do you know?
Well, there's not numbers at all, so it can't be numbers.
Exactly. If I'm looking for I don't give a shit what in an empty list, is it in there? No. That's an easy conclusion to make. If you give me an empty list and say, hey, can you check if? I go, no, it's not there. I didn't even tell you what. It doesn't matter. It's not there. It's empty. Can an empty list contain the thing you're looking for? No. That's what that first line means. That first line says, if you ever see an empty list, and the underscore means, and literally anything at all, it's false. Right? Great. That's easy. Right? Now the next line. The next line actually kind of has two parts. Let's focus on this part. All right? This right here is the syntax you use in Haskell to say, okay, you've got a list. In every list, we have the ability to take the head of the list and the tail of the list. Where the head of the list is the thing at the beginning, and the tail is everything after the beginning. Right? So let me open up like Notepad or something. If I have the list like A, B, C, D, when I have this syntax, what it means is, okay, I've got A and B, C, D. Okay? That's what that syntax means. So I've got my list, and I've got Y. Y is needle. All right? Y is the thing I'm looking for. So if I ever see a list that's not empty, and the thing I'm looking for, then what I'm going to do is I'm going to check, does X equal Y? Does X equal A? Or sorry, does Y equal A? Is A the thing I'm looking for? If it is, X equals Y evaluates to what? Yell it out. Wake up. Come on. True, of course. Right? So if the thing at the beginning of my list is the thing I'm looking for, X equals Y is true, we return true, we're done. But X equals Y might evaluate to false. A, the thing at the beginning of the list might not be what I'm looking for, right? So we've kind of established two cases here. The case, and I'm going to explain this to you, and I want you to think of this in context of what you're used to doing in your linear search. I started with the case of, is it an empty list? If it is, it's not there. Now we've got the case of, okay, is the thing at the beginning of the list the thing that I'm looking for? Yes or no? If it is, I'm done. If not, what do I do? What do I need to do if, okay, it's not an empty list, and the thing at the beginning of the list wasn't the thing I'm looking for? Am I done? No. What am I forgetting about? That's not a trick question. The rest of the list, the tail. A is the head, B, C, D is the tail. I forgot about that. But I've got some interesting news for you. It's not my problem anymore. I'm done. If I'm the function to do the linear search, all I want to do is check is it empty, and check if the thing at the beginning of the list is the thing I'm looking for. Otherwise, I'm done. I don't know. That's it. But you're left going, well, hold on. There's the remainder of the list. You got to look at the rest of the list. You can't just stop there. And I go, no, I am going to stop there. You know why I'm going to stop? Because, I don't know if you know this, I have a function that does a linear search for me. There's a function that will do a linear search for me. Does anyone know what that function's called? No. It's called linear search. But that's the name of the function I'm writing. I'm not sure it's sinking in. If your mind just got blown, you're paying attention. If it didn't, you're not paying attention. I just blew everyone's mind, whether you like it or not. I say, okay, are you an empty list? Yes or no? If you are, it's false. It's not there. Is the thing at the beginning of the list the thing I'm looking for? If it is, yeah, I'm done. If it's not, okay, I'm done. But here's what I'm going to do. I'm going to call the function linear search to search the list that's the tail. Everything else. Let's work through this. This is what I mean. So if A is not the thing I'm looking for, well, I call linear search on this list. Oops. What the heck is going on here? I just do the linear search again on XS, which is the tail. And I look for Y, which means, okay, is this an empty list? Come on, wake up. No. False, thank you. Is B the thing I'm looking for? Let's say it's not. Maybe it is. If it is, I'm done. But let's say it's not. Okay, so I just do the linear search again on the remainder of the list. Well, that's that. We'll take the head out. Is C the thing I'm looking for? If it is, I'm done. If not, do it on the remainder. Well, this is the remainder list, which if I take the head out of this, it's actually interesting. Really what I get is this. If I take the one thing out of a list, what's left? An empty list. So is D the thing I'm looking for? If it is, I'm done. If not, I just do it again on the tail of the list. Do I see an empty list? What does that mean? It's false. It's not there. I'm going to write this in Python real quick. Remember, this just means go from index 1 to the end, right? So this is head, tail. There. I wrote that code, that idea, but in Python. I check, okay, is it an empty list? Is its length 0? If it is, it's not there. Get the head and the tail. If head is the needle, return true. In fact, I can actually simplify it. Return. There. That's the same algorithm there. So let's say we say linear false. It's not there. Is 0 there? Yeah. Is 5 there? Yeah. What about an empty list? Yeah. It works. Now, does anyone know what we call this? Recursion. When something is defined in terms of itself. The definition of linear search contains requires linear search inside of it, which is weird. I haven't shown you this before, but this is totally valid code. And if you're like, whoa, this is a whole new topic, well, not really. Nothing about what I showed you is a new core underlying idea. If this doesn't make sense to you, take some time to understand this, because you absolutely can make sense of this. This is pretty neat. Any questions? All right, I'll catch you later. Remember, if you need any help, questions, thoughts, concerns, come to office hours. You know where to find me.